It's a pleasure to be here. Thanks to the organizers for inviting me. And it's very exciting to see all that's going on over here. I was asked to give an introduction to topological defects because topological defects can be sources for gravitational waves. And so I will be describing mostly topological defects, and then with some indication of the gravitational waves they can produce. So there are three lectures. So the first one is on kinks and domain walls. The second one is on strings, and the third one is on magnetic monopoles. So we're going to start with kinks and domain walls. The referencing in these lectures is a bit sparse, but I do have a list of reviews, some excellent reviews, solitons and instantons. Solitons and particles is a collection of papers, which is a beautiful collection. And then most of you would probably know about aspects of symmetry. Then there's a book by Vilenkin and Shellard, and then I have a book on kinks and domain walls. And most of the lecture will be drawn from the book that I have. But the focus here will mostly be on cosmology. Topological defects have lots of aspects to them, like quantum aspects and Fermi, how do fermions interact with defects and so on. I will mostly focus on the topics that relate to cosmology. And I find this beautiful, the quantum properties of defects. Unfortunately, we'll not be going into them. And the level of the lectures is intended for younger audiences. So I know that there are some senior people here. And so they may get bored, but hopefully there'll be something new for everyone. All right, so let's start with the simplest case, which you must have seen, is that if you have a scalar field with a lambda phi to the 4 coupling, then the Lagrangian is written in this way, the kinetic piece and then the potential piece. And so the potential is just this usual Mexican, or well, in this case, the double well potential, and it has this shape. And as you can see, there are two minima at phi equal to minus eta and phi equal to plus eta. And if you write the equation of motion for the scalar field, the classical equation is just the wave part plus this potential is equal to 0. And so this is the potential. For example, if you put phi equal to 0, then you get a minus lambda eta squared, and you might think that the mass is negative, but that refers to the negative curvature over here. Instead, the mass of the particles is given by the positive curvature over here at the true vacuum. And so what you do is you expand phi to be eta plus some small perturbation, and then you find that the mass of the particles is actually square root of 2 times m. Now I realize that I haven't explained m, but okay, never mind. Okay. But the important point here for us is that there's a solution to the equation of motion, which is eta, which is this expectation value, times tan hyperbolic of x, where this capital X is the Lorentz boosted coordinate. So what this describes is a solution which is minus eta far away to the left, and then it goes through 0, and then it comes back to plus eta. So on this diagram, you're starting at minus infinity over here, and then you're going over the hill and coming to plus eta over here. And so this solution is called the kink. And you can find the energy of this solution, and the energy density has this bell shape. And so it's all localized in a narrow region. You can find the total energy by integrating the energy density, and that turns out to be m cubed by lambda. where lambda is this coupling. And so that's interesting because the energy goes inversely as the coupling, which means usually in field theory, you take the coupling to be small. But if lambda is small, then the energy is large. So you have a large energy object, which is just sitting in one place. Sitting, in this case, is just sitting, but you can also boost it, so it can start moving at a constant velocity. And the width of this is given inversely by the mass. So this solution describes something that's rather well localized, and it just can move back and forth. I mean, it can be Lorentz boosted. And it's very heavy. It's a very heavy object. So this is called the Kinks solution. And there are lots of different models. For example, the sine-Gordon model, where you take this potential and you get a solution which has similar properties. Now, there is one very nice way to find the solution, because it's a rather non-intuitive tan hyperbolic type of solution, and that's called the Bogomolny method. So what you start by doing is you write the energy as an integral, and then here's the kinetic energy part, here's the gradient energy part, and then there's a potential. But you write it in a different way. You write the kinetic part, which is down here, and then these two you write as a whole square. So you have a gradient of phi, and then the square root of the potential, the whole thing squared. So now when you whole square it, you will get the dx phi squared, and you will get the v phi, but you'll also get the cross term, the dx phi times square root of 2v phi, and that you subtract off. Okay, so that's the way. Then what you realize is that you can separate this as the first two terms, which is over here, and then the last term you can separate out. And instead of thinking of this as an integral over dx, you can think of it as an integral over d phi, because there's a d phi by dx over here. So you get an integral d phi and then the square root of 2 times the potential. And this integral you can do, for example, in the last case, where v is this thing whole squared, when you take the square root, you will just get phi squared minus eta squared. And so you can do this integral quite easily. And then the minimum of the energy is when these whole squares go to 0. So dt phi is 0. And then this one tells you that dx phi is just square root of 2 times the potential. And that's quite easy to solve, because the first order differential equation, you can just divide and integrate. And the energy, so now both of these two terms are 0. So the energy is just this last term. And so the last term is just d phi root 2v. And that turns out to be the energy of the kink. So this is a very clever way to get a solution. And this simple example is in 1 dimension, but it works in 2 and it works in 3 dimensions as well. So it's a very useful technique to know. But here we are kind of more interested in not in a particular solution, but in the general features of the field theory that give you such a solution. Okay? So if you think about it, all that was required for the solution was that there be 2 different minima of the potential. Okay? That was all. And so all that you require is that the model has multiple disconnected degenerate vacua, meaning they have different points which have the same energy, same lowest energy. And so this could happen for a variety of reasons, but generically, whenever you have a degeneracy, it's due to a discrete symmetry. Okay? So there is some symmetry in the model that is telling you that there are more than one vacuum. Yeah, there's more than one vacuum. Sorry. And then when the symmetry breaks, right? So when you say phi is eta plus psi or whatever, then that implies that there's a domain wall solution. In the last case, it was very easy to see what the symmetry was. It's just that when you change phi to minus phi, then the Lagrangian is invariant. And so that is the discrete symmetry. And that discrete symmetry is just called the Z2. And so this symmetry breaking over here is that the Z2, or the Z2, whatever you wish to call it, is Z2 is breaking to 1. Okay, so this is the symmetry breaking. And whenever you have such a symmetry breaking, you will have domain walls. So you kind of can forget about the tan hyperbolic, the phi squared minus eta squared whole square. Forget all that. You just think about the symmetries in the model and how the symmetry breaks. But even if the symmetry is not perfect, for example, you have the Z2 model over here, but then you add a small term, epsilon phi cube. Okay? So if epsilon is 0, then you're back to the Z2 model. But if epsilon is not 0, then the potential looks slightly tilted in this way. Okay? So even in this case, you have different vacua. They are not exactly degenerate, but they are still there. And you can have objects which go from here, go all the way to the other side. Okay? Now, in this case, there is no static kink solution, but there are approximate kink-like objects, and I will call them biased kinks. And in fact, for cosmology and for gravitational waves, these objects are equally important in some ways. Okay? So this is quite generic, that you have any potential which has different, several disconnected minima that need not be degenerate, and then you will get these kink-like solutions which will be biased, but they may still be important in cosmology. Okay? And in fact, we will look at specific particle physics models, and you will see that these biased domain walls should be very common in any in sort of grand unified models of particle physics. Okay. So that brings me to consider a grand unified theory. So this would be, say, SU5, which is the minimal grand unified theory. The bosonic sector, like just the bosons, not considering the fermions, consist of a scalar field, phi, and the gauge fields x. Okay? Now, phi is in the adjoint representation of SU5. So it's really a matrix. So phi is some 5 times 5 matrix. Yeah. And the Lagrangian is just, again, the radiant energies in phi, the F mu nu, which is the E squared minus B squared for the gauge fields, and then the potential. And the potential is the most general quartic potential. So it has trace phi squared whole squared, trace phi to the 4. You can have a trace phi cube, and then there can be a constant term. And so you can start by thinking, let's say, what happens if I put gamma equal to 0? Okay, so this term is absent. And then there is an additional symmetry. So this model has an SU5 symmetry. So I don't know if the students, are you familiar with symmetry groups and SU groups? Yes? Okay. Anyway, so this model has SU5 symmetry, but if you turn off the gamma, if you turn off the phi cube, then there's an additional Z2 symmetry, which is phi to minus phi, right? You can flip the sign of phi, and you still get the same Lagrangian. So then the symmetry breaking that I have up there, the SU5 going to SU3 cross SU2 cross U1, remember the 3, 2, 1 is the standard model symmetry. And that happens if this phi gets a Vev, gets a vacuum expectation value, which is proportional to 2, 2, 2, minus 3, minus 3. Okay? Because then in this sector, in this corner over here is the SU3, it's the 3 by 3 matrix, and so you can do 3 by 3 transformation. This is proportional to the identity, and this is proportional to the identity also, but this is a 2 by 2 matrix, and so this is the SU2 part, right? So then you have SU3 and SU2 sitting in here, and then the U1 is just that this matrix commutes with itself, so that gives another U1. So that's how SU5 breaks to SU3 cross SU2 cross U1 if you give this Vev. The discrete factors down here are important, but at the moment, let's just ignore them. So I'll come back to that later. Okay, so now you have an additional Z2 symmetry that gets broken, right? So if you choose phi to be this, then phi to minus phi is no longer a symmetry because you've chosen this particular value. Just like in this case, you could choose phi to be plus eta or minus eta, but as soon as you do that, you've broken the symmetry. Okay. So here also, as soon as you choose 2, 2, 2, minus 3, you've broken the symmetry. And since the Z2 symmetry is broken, you will get kinks in this model. Okay? So remember, I'm not solving any differential equations. I'm not doing anything of that kind. Just based on symmetry, I can tell you that there are domain walls in this model. Okay? And so what you can do is you can take phi to be minus 2, 2, 2, minus 3 on the left-hand side, and phi on the right-hand side to be minus of this thing. So that'll be plus 2, 2, 2, minus 3. And then with these boundary conditions, you will automatically get a kink-like solution. Okay? But life is not so simple. Let's say I choose phi minus to be this particular value. What you can show is that if you have a solution, then if you choose this on the left-hand side, then on the right-hand side, this phi plus minimizes the energy only if phi plus commutes with phi minus. I won't go into the details of the proof of this, but you have to choose boundary conditions that actually commute with each other. So then, if you choose phi minus to be this, then there are 3 classes of solutions. One is that you just take this and you multiply it with the minus sign. That's the minus 2, 2, 2, minus 3. The other is that you take a minus sign, but then you exchange one of the elements. So you've got 2, 2, minus 3, 2, minus 3. Right? And the last one is where you exchange 2 of the elements, minus 3, and 2. Right? So you not only flip the sign, but you do an SU5 rotation as well. So there are 3 classes of solutions. In fact, they can be written in a very nice way. This phi in class Q, where Q is 0, 1, 2, depending on how many things you permute, you can write it in terms of phi plus phi minus by 2, phi plus minus phi minus by 2. So these are these 2 matrices. And then these have some functions in front of them. And then this last matrix is actually 0 for Q 0 and 2, but for Q equal to 1, it is given in this way. I won't have time to describe how to get this, but in any case, there are 3 solutions, and then the 3 of them can all be written in this way. And so, and these functions in front define the boundary conditions. So for example, f minus of q is minus plus 1, minus on the left and plus on the right. F plus is plus 1 everywhere. G is 0 on the boundaries. So a solution might look like this. This is F minus. F minus might do this. So that's the kink. F plus is flat, but it has some wiggles over here. Then it's flat. And then G is 0 far away, and then just has some wiggles in the middle. So these are 3 different kinds of domain walls in this SU5 model. Okay? So this is a grand unified model, but you have 3 different kinds.
This 5 plus 5 minus, if you have these kind of solution, that means you still have standard model on each side of the domain.
Yes, but a different a twisted standard model. Yeah.
But the other solution that you got, that breaks the standard model also on each side? That still is the standard?
That's still the standard model. It's broken in a different way. It's that the boundary, a group of authors put this as a clash of symmetries. That you have the standard model here, you have the standard model here, and the 2 have to meet. And so there's even though the groups are the same, they don't quite meet, and so you have a reduced symmetry on the wall. No, because they're protected by topology. So there's no way to get rid of them except that you annihilate it with an anti-wall. Yeah.
So the scale is like gut scale.
Yeah, these are gut scale. But it turns out that it's even richer than what you had thought. It's that even you can have solutions which are not topological. So the solutions I was telling you were that phi takes some value here and phi takes negative value here. So then you have to go from plus to minus. But even if you stay all plus, you can write down solutions, non-topological kink type solutions, very similar to what I wrote before, but with some signs are different. In the topological case, I had F plus, M plus, F minus, M minus, but now I have F minus, M plus, F plus, M. So there are some sign differences, but you can get non-topological kink solutions in the same model. The issue is that the non-topological solutions are generally unstable, but they are still solving the equations of motion. Now, so I'm trying to convey that, I'm trying to convey that these domain walls are very generic. They're very easily found in models, in complicated models like grand unified models. And the second thing I'm trying to convey is that there are many types of domain walls in that same model. And so the situation, if you want to study exactly how gut symmetry breaks and what gravitational waves are emitted, you have to worry about all these different kinds of domain walls as they are formed, as they're interacting, as they're evolving. So, for example, another complication is that I told you that there are 3 classes of solutions, the Q equal to 0, Q equal to 1, and Q equal to 2. The Q equal to 1 solution results from a 6-dimensional set of boundary conditions. So remember, back here, so what I have to do is that if I take 2, 2, 2, minus 3 on the left, then on the right, I have to switch a minus 3 and a 2. Okay? So I can either switch the minus 3 with this 2, or this 2, or this 2, or I can take this minus 3 and I can switch it with this 2, or this 2, or this. So there are 6 different ways I can switch these things. And so I have a 6-dimensional space of boundary conditions that will give me the Q equal to 1 solution. Okay? But if I take the Q equal to 2 case, then I have to switch two of the 2's with the 2 of the minus 3's. So I can choose these 2 2's or these 2 2's or the first and the third 2. So that there are a smaller number of boundary conditions that give me the Q equal to 2 solutions. So the Q equal to 1 solution results from a 6-dimensional set of boundary conditions. But the Q equal to 2 solution results from a 4-dimensional set of boundary conditions. However, so you would think that Q equal to 1 is easier to form because there are more, it has more possibilities lead to the Q equal to 1 solution. But the Q equal to 2 solution has the least energy. So from this, it seems that what's going to happen when you have this gut phase transition is that you'll form a Q equal to 1 wall network that will then decay into a Q equal to 2 wall network. So one type of wall will start decaying into the other. So then you have to worry about the consequences of that. So the general picture is something like this, that this is the Z2 symmetry. So you have some minima on the left, you have some minima on the right, and then you have to go from the minima on the left to the minima on the right, and that gives you a topological kink. But there are many ways to do this. You can go from this point to this point, any of these 10 points on this side, and each of them is giving you a kind of a kink. And then the non-topological kinks that I was talking about were actually going from one within one side. So you don't flip the sign, but you stay on one side. So that's the sort of general picture, that you have so many possibilities just in this grand unified model. But life can be even more interesting. So actually, just to clarify that, that this picture actually holds for SU5, but the stability properties of the domain walls change because of the gauge fields. And so this model we've analyzed more in a non-gauge case. I won't go into the details, but yeah, it's in a sort of a discretized version of the SU5. So okay, maybe I'll come back to that in just a minute. So there's a possibility that you start at this point, and then you go to some point over here, and then the next you come back over here, and then you can do something like this, and then eventually you come back here, okay? So for example, you can do minus 2, 2, 2, minus 3, minus 3, then you switch the sign, so that becomes a plus, and then you switch two of them, so you get 2, minus 3, 2, 2, then you switch the sign again, and you do some permutation, you switch the sign, do some permutation. So you can imagine this kind of diagram where you're going from one minimum to another, to another, to another, and so on. And in this case, the funny thing that happens is that if you go from here to here, that's a kink, let's say. You go from here back there, that's an anti-kink. Generally, kinks and anti-kinks attract, and they like to annihilate. But if you don't go back to the same vacuum, then they actually repel, and they can't annihilate. So as a result, you might have what are called kink lattices. You can have one, this kink is the one that goes from here to here. This is an anti-kink going from here back to the first place, to the first set. But the red can't annihilate the purple because they are twisted with respect to each other. Okay? And in this way, you can construct twisted kinks. And if this space is compact, then what you will find is that this becomes a lattice of kinks, which just sits there, and it doesn't go away. So you if in this system you do a phase transition, you break the symmetry, you will end up with a lattice of kinks. It turns out that in the gauged SU5 model, this lattice is not stable. It's still a solution, but it's not stable. But when I discretize the model, that SU5 becomes a permutation group, S5 actually, then it is stable. So now what you do is you imagine, so here's the space. Now what you do is you imagine that you impose periodic boundary conditions, okay? So then this line is like a circle because it's periodic. Sorry, you have a question? So the non-topological kinks, you jump from here to here. Yeah, you'd be jumping in the same sector. Actually, I don't know what happens in that case. But the problem with the non-topological kinks is that they are unstable as it is, so they might just dissipate. Yeah. All right, so coming back to compactifying the spatial dimension, you can make this a circle. And now you ask what happens to this lattice if you're on a circle. Then you get this picture where the kinks, so this is the circle, this is space, and then the kinks are like this, right? So here's the lattice on the circle. But then if you were to do it in 2 dimensions, then these domain walls would have to come and meet at some point, and that point would become a node. And now if you go to 3 dimensions, then you can kind of pull this out, and then so you have domain walls which are meeting in junctions like this, right? Have different what? Yes, yes. You mean how does this node, what this node looks like? It's difficult to say because inside the kink, it's something else. So the vacuum is only between the kinks, right? Here and here and here and here. Inside the kink, the phi has some other value. It's not 0, by the way. It's not, phi doesn't vanish at the center of the kink. Okay, so keep this in mind, and we'll discuss the dynamics of domain walls, and then maybe I'll come back to this lattice once more. So the question is, if you have a domain wall, how does it move? Okay. So you can say, well, I know the field theory. I am just going to solve the full field theory, and that will tell me how the domain wall will move. And that's a perfectly good way to think about it, except that the field itself has many degrees of freedom, like radiation and small excitation, and you may not be interested in the detailed dynamics of the whole field. You are just interested in how this wall is moving, right? So for that, there is something called the Nambu-Goto approach, right? Where you say, you just want to get a Lagrangian or an action that describes the motion of the wall, and you want to ignore all the radiation and everything else. So for that, you say the position of the wall is this capital X as a function of time and 2 spatial coordinates. So because remember, you have some wall, some piece of wall, then a point on the wall is described by two coordinates, right? Which are over there, zeta and chi, right? And then there's the time-like, dimension. And what you can do is you can say, you can take any arbitrary point in space. So here's the diagram. You take some point in space, and so the vector to this point is this long vector over here. you can think of it as a point on the wall, and then a vector from the wall to that point. So that's x mu is this capital X. This is the vector to the wall, and then there is this. This is the vector from the wall to that point. And you can rewrite the action, the field theory action, in terms of these new coordinates, xi, tau, chi, and chi, zeta and chi. And basically, all that you're doing is that when you go to these new coordinates, these worldsheet coordinates, then the Lagrangian of the fields becomes a function of this capital X, because this is assumed to be, you take to be small. And what you derive from it is what's called the Nambu-Goto action, that the action is just minus sigma, which is the wall tension, times an integral over the worldsheet coordinates times the square root of the determinant of the worldsheet metric. So everything is described in terms of this capital X. Of course, this is the leading action. Then there are other terms, but the other terms are assumed to be small. So maybe let me just say this once more. The action for the wall is given by this, where this metric, this is the determinant of the metric, and the metric is given by the background metric, the ambient space metric, times the derivatives of the world, actually the world volume in this case, right? So this is how you find little h, a, b. You take the determinant, and this is the action. So the Nambu-Goto action, what it does is basically assumes that the wall is very thin, okay? That the thickness of the wall is not important, okay? And then you can just treat it like a membrane, like a surface that is moving around. And from the action, you can derive equations of motion. A little complicated, where this is the Christoffel symbol of the background. Christoffel symbol of the background. In Minkowski background, gamma is 0, so then the equation simplifies a little bit. But I don't think this action is very useful because this equation and the action, the approximations, fail when the walls intersect each other. When two walls get very close to each other, then the thickness becomes important. And if you have a two-dimensional surface, two-dimensional surfaces moving around in space, then they're likely to get very close to each other, hit each other, and then field theory effects will become important. So this is maybe the validity of this equation is very limited, at least in 3 dimensions. So there can be sort of singular points, like you can have places where the wall becomes very sharp, or two different walls come together, or you can have bends in the wall, and that's when this approximation will fail. You can also get very intense radiation from some of these points, and then again, in deriving the Nambu-Goto action, you've ignored the radiation. So that's again is not a good thing to do.
So as far as the thickness is concerned, so at what level it breaks down? So it's also connected to the scale of motion, right? So
yeah.
Connect like thin wall approximation for what might be.
So the thickness is given by the inverse mass of the particle. So they have to come close, that close. But two walls, when they come, they're going to hit each other, right? They can't cross without hitting. So the width becomes important.
So even if we ignore the interaction, then thin wall will be valid or will break down at some point.
So if you ignore the interaction, then the walls will pass through each other. But in real life, that doesn't happen. What happens is over here, you have two walls, pieces of walls. This is my artwork. This two walls come together, and then they will reconnect at this point, and they will form something like this. So they form a wormhole, if you wish, by coming together. And this can't be described by the Nambu-Goto action. So in a way, if you want to find gravitational waves from domain walls, then I think you're better off solving the field theory rather than the. I mean, in the case of strings, something similar happens, where two strings come and then they reconnect. But there is one point, and you can kind of fiddle around a little bit and reconnect it. I don't know how you would do it over here. It seems a more complicated thing to take reconnections into account.
But in this, we can calculate the energy on each side, like before and after.
Like
So
over here and here.
Yeah.
Yeah.
And then you know that this much energy was released per horizon, and from that you can estimate what the
So if you're studying the exact, well, okay, so radiation, so Nambu-Goto doesn't take into account radiation at all, because it just restricts the degrees of freedom to the wall degrees of freedom.
So what I meant was there's a difference in energy that has to go somewhere. So you think that energy would go into gravitational waves.
Oh, okay.
So it's just like a phase transition that you have a tunneling from one vacuum to other. So you just have that latent that energy difference released as gravitational waves.
So in this reconnection, you'd also emit scalar particles.
Yes.
So you have to worry about that. Yeah.
But to calculate gravitational waves, probably you don't need the dynamics of how the reconnection takes place. You just need the.
So you'll probably have a whole network, like a universe full of domain walls moving around. So I think it's a little complicated to. Yeah.
So it's not like one domain wall per horizon.
There'll be it's actually, I don't know what we mean by one, because if you study the formation of these walls, then it is one, but it has a very complicated topology. So like you might have some wormholes, and they might go, and then there might be other wormholes. So it might be, it's very complicated, yeah. But there are some solutions of the Nambu-Goto equations that people have found. One of them is a traveling wave. So you can have a domain wall, you can put a little bump on it, and this bump can move forward at the speed of light. If z is the coordinate with respect to the plane, then there are solutions which have this dependence on them. And the nice thing about traveling waves is that at least in the string case, you can show that traveling waves are solutions in the full field theory, not just Nambu-Goto, but the full field theory, and not just the field theory, but even when you include gravity. So it's the solution of the Einstein abelian Higgs model in that case. In the domain wall case, things might be a little tricky, and we'll come to that in a bit. But the traveling wave is a solution even in field theory, and I would think with gravity included, but I'm not sure. And I don't think anyone has resolved this question yet. Then, of course, you can have domain walls that look like cylinders, and so that would be a solution for a cylinder. You can have a sphere, you can have a spherical domain wall that'll collapse, and the radius collapses in this way. You have to do this integral. You can have a sphere in de Sitter background, which is stationary, and so if the radius is given by the inverse Hubble scale, then you just have a domain wall which is sitting still in de Sitter space. It's unstable, nonetheless, it's a solution. And then finally, you can have a catenoid. You can have this kind of solution. RZ is 1 over alpha Ghosh alpha Z. So that's also the solution of the Nambu-Goto equation. Now, it's not clear which of these survives in the field theory. The traveling wave does, but I don't know about the others.
These solutions don't have a classification in terms of symmetry.
The traveling wave, of course, you can take any pulse shape you want, and it will be a solution. In terms of symmetries, or you mean?
Like in the beginning, you said that symmetry breaking the Z2 into 1 tells you there is a domain wall.
Yeah.
Similar things cannot be.
No, not that I know of. Because, okay, so these are solutions in Nambu-Goto where you've kind of dismissed all the field theory and you're just saying that here is an object and I want like a relativistic object, a membrane, and I want to describe how it moves. So, yeah. So now you ask what's the gravitational field of a domain wall. So, so the energy momentum tensor, so again in the Nambu-Goto approximation, is going to be just 1, 0, minus 1, minus 1, and a delta function for, this is at x equal to 0, that's where I've put the domain wall. Then these authors, they found the metric. It looks like this. There's a 1 minus kappa capital X squared dt squared, so on, where capital X is basically related to little x in this way. And this kappa is the parameter which depends on Newton's constant and the wall tension. So if you take little x to be constant, so then the dx goes away and this capital X is a constant, then you can see that, that this is dt squared minus this exponential 2 times kappa times t, dy squared plus dz squared. So that's like de Sitter space, like this wall, the inside of the wall, the wall is inflating in the transverse directions. The other thing you can do is maybe take constant y and z, so then these go away. And then you can rewrite this as d tau squared minus dc squared. And here are the transformations from tau, from t and x to tau and c. But then you find that the domain wall is, so this is Rindler. This is a Rindler space. So that means that particles have constant acceleration. And so if you take a particle at constant capital X, then it is actually accelerating away from the wall. And so what this is saying is that particles are repelled from the wall with constant acceleration kappa. Okay? So if you have a wall, then gravity is not pulling things into the wall, but pushing them out. Okay? So this is sort of repulsive gravity. Okay. But there's another interesting way to look at this metric. So here's the metric again. And then what IISER and Sakivi showed was that you can do a coordinate transformation such that this becomes a Minkowski metric. But then the location of the wall is at x squared plus y squared plus z squared is equal to times squared plus a constant. And this actually describes a bouncing spherical wall. So you started out with a planar wall, but in these coordinates, it looks like a spherical wall, which comes in, bounces, and then goes out. So it's a bit confusing. I mean, how all these pictures mesh together. But one thing is clear, that, that particles are repelled from the wall. Okay.
Take perturbations about this metric. That would describe your gravitational wave generated by the TE.
Yes. Yeah. So then you can ask, well, all these metrics were found by taking the thin wall approximation, which is the Nambu-Goto approximation. what happens if I take the full field theory and take thick walls? Well, not much changes, unless you go to very high tension. So this eta squared is basically like the sigma. So unless your G sigma is larger than something, not much happens. But what happens when G sigma becomes large? Then you get something called topological inflation. And the idea is simple. Here's the potential. The wall goes from minus eta to eta. So there's always some part of space which is sitting on top of this potential. But if this height is high enough, then this has a lot of vacuum energy in it, and it starts inflating. So what you have is that the inside of the wall is actually inflating and getting bigger. Yeah? But then you ask, but this is now eternally inflating, because you have a wall that's sitting there, and this is always inflating. So then the graceful exit problem the solution to the graceful exit problem is that if you're slightly to the side of this center, then that region will keep slipping and will come down, and so you will end inflation in a given region of space. Anyway, this is topological inflation. The other thing to discuss is the spherical wall. And again, IISER and Skivi found the metric. And so you have the wall over here with the radius capital R tau. Then you know that inside the spherical wall, the metric has to be flat, right, by Birkhoff's theorem. So inside is Minkowski, and outside it has to be Schwarzschild. So outside is Schwarzschild. So the inside of the wall, you can write the flat metric in terms of some time coordinate capital T. And then outside is the Schwarzschild metric in terms of another time, little t. But little t and capital T have to agree on the wall. So there's a matching condition. And that is given by where the wall is located. And so there's a relation between capital T and the radius of the wall, and similarly between little t and the radius of the wall. And if you calculate the mass in this Schwarzschild metric, you find that it is 4 pi sigma times r squared. So that's what you would expect, right? Because that's just 4 pi r squared, the surface area times the tension. But then there's a correction factor, 1 minus 2 pi grm, which is due to the self-gravity of the wall. Anyway, this solution is also known. And of course, this spherical wall will collapse to form a black hole. All right. So now let's come to cosmology. And maybe I skip this because it's not very important for us. It is important, I know, for some of the talks over here, that you would have phase transitions in the early universe. It could be a first order phase transition or a second order phase transition. But anyway, the details are not that important for us. Basically, all that we need is symmetry. With symmetry, all the degenerate vacua are equally likely. So all that you have to do is to populate space with random choices of the vacuum. For example, in the Z2 case, you can have two vacua. One is black and the other is white. And so you throw black and white randomly on a lattice, and the picture looks something like this. Okay. Then you say, I see clusters of black. So like 1, 2, 3, 4, this is a cluster. This is a cluster of 1. And then there is this huge cluster. So let me count how many clusters there are of a given size. Of size 1, it turns out to 462, 2, 84, 3, 14, so on. And then you come down to 1 cluster. And then there is 1 cluster of 31,082 of these cells. So basically, all the walls are in this one infinite cluster. I mean, this is on a finite lattice. If you take it to be infinite, then you basically, this phase transition forms one giant connected domain wall with some complicated topology. I get till 11? Okay. All right. So then we've done this simulation, this kind of simulation for the models that I was describing earlier. So we start with some thermal distribution of a scalar, of the scalar fields of this phi, this kind of scalar field, and we relax it, and then we end up with a kink lattice, just as I showed. So, so this is a field theory evolution. So in this way, you can study the formation of kinks and kink lattices. In 2 dimensions, we get a picture like this. So there are nodes over here, not so clear maybe, but if you look over here, then there are several domain walls coming together at this node. So this is just confirming the picture that I showed earlier. If you compactify this space and this space, both of them, so there's 2 spatial toroidal dimensions, then you end up with a lattice of domain walls, which looks like this. So, but there are severe cosmological constraints on domain walls. I mean, the simplest constraint comes from finding the relative energy density in domain walls. You take the wall energy density, divide by the critical energy density of the universe. So that is one wall, even if you assume there's one wall of area of the Hubble length squared, so that's cosmic time squared, sigma t squared, and then you divide by the volume t cubed. So that's the energy density in walls, and the critical density is given over here. And when you estimate this, this comes out to be g sigma times time. Sigma, remember, is the wall tension. And if you assume that lambda is order 1, and you require that the energy density, the ratio of omega in walls is less than 1, then what you find is that this eta, the scale at which the symmetry breaks, should be less than 100 MeV. But 100 MeV is like QCD scale. So, and we think we know field theory, the particle physics quite well at 100 MeV. And so this seems to be ruled out. So you can't have walls in the present universe. The other constraints, there might be other constraints on CMB, BBN, etc., and they may be even tighter. So there seems to be some sort of issue that on the one hand, I said that this domain wall in SU5 seems very common, seems very easy to get. As long as you have different vacua, you will get domain walls. So from the particle physics side, it seems very easy to get domain walls. And on the other hand, from the cosmological side, it seems that you can't have them. So is there a fix? Well, the fix is simple, that if the discrete symmetry is approximate, so if the phi cube terms are still there, but they're small, then you will form the walls exactly as you would form when the cubic term is not there. I mean, so that's true if the cubic term is small. Then the walls will survive for some time, exactly moving in the Nambu-Goto way. But at some time, the imbalance of the different vacua will come into play, and the walls will all start moving to one side, and they will annihilate, and the walls will go away. And you can calculate the time at which the wall decays, and it's the formation time divided by that coupling constant squared, that gamma squared. This is remember, this is a gamma trace phi cube. So this is a gamma in there. So the walls are there for some time in cosmology, but then they go away. And that's the interesting scenario for gravitational wave production. You have to find gravitational wave production biased domain walls. So coming to gravitational waves, this domain wall network will emit gravitational waves. I think you'll hear more about it in later talks. And the gravitational waves will become a stochastic background. So again, in that picture where the walls are colliding, then you get gravitational waves coming out. A simple estimate, the kind of estimate that was made in the early days, is that you use the quadrupole approximation, and then the power emitted is this g by 5, and then the third derivative of the quadrupole moment. But the quadrupole moment is basically mr squared. It's the mass involved in the collision and the size squared. And then the three derivatives, the dt cubed is an r cubed, assuming that the time scale is given by the radius of curvature of these walls. And so you get an estimate 4 pi sigma whole squared gr squared. So that's the power emitted by these domain wall collisions. Of course, this assumes that the time scale is r, but the wall thickness is another scale in the problem, and it may play a role. I think this paper is referring to that time scale. Anyway, I hope to hear more from the experts at this workshop. I know there have been field theory simulations of these domain wall networks, so it'll be interesting to hear what they get. But let me close up by once again emphasizing that biased domain walls occur very naturally in particle physics, and that would imply their existence in cosmology, even if it's for a finite duration. And then the network, the evolution is quite complicated because you might have these junctions and all these complicated objects. Later on, I'll also discuss that domain walls could erase other defects, like magnetic monopoles, and I'll discuss this in lecture 3. And then these domain walls will give a stochastic background of gravitational waves, and that could be of interest to observations. So I'll close with that. Oh, there's one. Sorry, you're referring to, let's see, this one? Yeah, so this is the radius. So, yes. Yes. So this is just a constant. This is a minimum radius of so it comes from, this solution looks like it comes to a minimum radius and then bounces back. Yeah. This, yes. So of course you can have models where Zn just breaks, and then you will have these many walls coming together and forming junctions. So that's another situation. But the funny thing here is that even if I don't take the Zn, this is just SU5 cross Z2, I am getting some similar structures. Oh, I see. I mean, the evolution will be different, and I think the gravitational wave signatures will be different. So that would be interesting. Yeah.
So any other questions?
Is it necessary that that it should be the biased domain wall if it is stable, like topologically stable domain wall?
If it's then it's ruled out by cosmology, no?
Yeah.
That omega, so you have to bias them.
And another question is, if it is biased, the Z2 is not there. So how there will be formation of domain wall on the first place? Like I can like see that there will be a solution, like kink-like solution, but in the real space, like when the phase transition will happen, so after some time there will be some kind of like possibility of uh, two different non-degenerate vacuum. But why the universe will not choose the true vacuum till like because if like till when it will approach the Ginzburg temperature, so during the quantum fluctuation era, so it may seems like if this bias term was quite large, then there will be no formation of domino.
It's a quantitative question. I mean, so if they're exactly degenerate, then the probability is half and half.
Yeah.
If it's slightly different, then maybe it's 0.6 and 0.4 or something. If it's very different, then it might be 0.01. So it's a quantitative question.
So is there any study about that? Like
there was a paper by Subir Sarkar and Larson, and this was many years ago. I can dig up the reference.
okay,
Yeah.
thank you. Thanks.
Yeah. But there have been later papers as well.
So is biasing is the only way for vanishing the domain wall solution or for sustaining? Because if you are saying that for SU5 models, so there are some certain class of domain wall solution which cannot annihilate each other.
Yeah.
But there can, in general, there is a wall solution and there is an anti-wall solution. So they can pair, annihilate, and go ahead.
Yeah,
Right?
so actually in SU5 in the gauge theory, that's not an issue because there's an instability of the lattice, so they will end up annihilating. Maybe I didn't say that very clearly. So in gauge SU5, there isn't that issue. Sorry, what was the question? Okay.
So is biasing is the only
Oh, so there is another solution, which is that if you have a wall, you might be able to nucleate a cosmic string. So then basically make a hole in the wall, and then the
through
hole
that it
starts
will
spreading,
spread.
and then it eats up the wall, and then you're left with a string. That might take some engineering from the particle physics model building to have walls and then have strings eat them up. It would take some model building. I actually, maybe Andrew, do you know any? Huh?
Walls bounded by string, Anish.
So in your model, do you form walls and then they get eaten up by? Yeah. So yeah.
There is another way recently studied in the literature by the same group, Ferreira and I think from Czech Republic. They found that if the wall tension varies with time, let's say you cook up a scenario where wall tension is not constant over the entire universe, it varies with time. Then also you can decay away the domain wall instead of having a bias term.
Right, but I think of all the solutions you mentioned, I think the biased one is the most natural.
Yeah, true. But then people try to ask like, what is the justification of having a bias from a BSM model, right? What operators you could write down, what kind of BSM physics you can write down that could
Well, a
lead to this bias.
phi cube is pretty natural, no?
Yeah, but then you cannot only choose phi cube, no? You have to choose all the like you have to create a hierarchy between the phi cube and phi fives, and then little bit of fine tuning involved. So I have one more question. So in one of the slides you had time of formation equal to time decay by gamma square, right?
Right.
So gamma is a dimension full parameter?
No, gamma, oh, I see what you're saying. Yeah, that.
So it's a dimension full parameter, right? So if gamma is a dimension full parameter, then
No, okay, so I must be missing something. Mass scale because gamma pi cube gamma would have dimensions of mass. So yes, there's something missing. Yeah.
So this, I have a quick question. So the simulations you were showing, so that takes into account the radiation also, or?
Yeah, so that's a field theory simulation. Like these, yeah, so these are field theory simulations. It's actually a Langevin type where you have because we start with a thermal system and then sort of cool it. So there's a noise term, and so it's a field theory simulation. Yeah.
You mentioned the quantum nature of these effects.
Yeah, I mean, it's most interesting in the case of magnetic monopoles, where you can have all sorts of interesting, for example, Bayer number violation could happen in magnetic monopoles. There could be dions, there could be fermions. Magnetic monopoles can be fermions, they can have spin half, even though they are made with bosonic fields. Yeah, and maybe if you have a theta term, then they can get a fractional charge. All sorts of beautiful properties.
Quantum nature comes from this Arno-Bohm kind of phase when you go around that effect.
I think it's actually lots of different things happening. For example, I mean, the thing that I just mentioned, that you start with a scalar field, spin 0, and a spin 1 field, and then you form a monopole, and that can become spin half, which is quite interesting. It's a different kind of, but that book that I mentioned earlier, I'll write in the solitons and particles book, that has a lot of beautiful papers on all kinds of solitons. It's a bit dated now, but it has lots of beautiful papers that are fun to read, and they have commentary at the beginning, and so you would enjoy that a lot. Let me bring that up. This book, Solitons and Particles.
I have a question here, backside. So you said that in the SU5 case, you can have like 2 or more kinds of domain walls. And then you said that, I mean, one of them could be unstable and one of them could decay into the other kind. Are there any criteria of how that decay happens? I mean, is like whether one of them splits into 2 of the other kind, or how does it happen?
I think one of them would probably split into the other plus a non-topological wall. And then the non-topological wall would be unstable to something else. I'm not sure, but that's what would happen.
Work of such walls, and then, I mean, the one with higher surface tension can also shrink, right? Because it is attached to a one with a lower surface tension.
So I was thinking just in one dimension. So this is like, so then it's not attached to anything. It's just a free wall. Right. But if you take that, if you take the most common, most easily obtainable wall, it will decay into the least energy wall, and then maybe it will emit a non-topological wall, which will then dissipate somehow, I don't know. So, yeah. Because the distinction, let me just show that. So, well, maybe this is not quite, yeah, so it's, yeah, I don't know how to explain that. But it's the Q equal to 1 wall would be to go from here to here and then have a non-topological wall.
So we'll take one last question because you have to meet again at 11:30 after coffee.
Sir, in that scenario where you talked about Q equals 1 would have this boundary condition, which is a 6-dimensional set, and Q equals 2 would have a 4-dimensional set. However, Q equals 2 would be a lower energy solution. So Q equals 0 is also a possibility. And but like that will then decay to Q equals 2, like 0 is the highest energy solution, like
Q equal to 0 is the highest energy solution. And you can kind of see that quite easily. Let me just take a minute. So you see, you're going from here to here. So this is the Q equal to 0 with a minus sign. Yeah. So 2 has to become minus 2, 2 has to become minus 2, 2 has to become minus 2. And then here minus 3 becomes plus 3 and so on, right? So every entry is changing, is doubling up, right? So that's a lot of energy. But if you go from 2 to this solution, and the first one, 2 goes to minus 2, the second one, 2 goes to minus 2, and then the third goes from 2 to plus 3, which is less of a change. So it has a little less energy. And then if you check this last one, then it's 2 goes to minus 2, 2 goes to plus 3, 2 goes to plus 3. So the least change is happening when you go from here to here. And that is what is saying that that's the lightest. This one is the next one, and this one is the heaviest.
So with that, let's thank Tanmay for that excellent talk. And we'll meet again at 11:30.